Today we're going to do a few problems that deal with what's called optimization, finding an optimal solution for a function. So let's jump right into the first example. Let's say we have two vertical posts. One of them 7 meters tall and the other is 13 meters tall. They're going to be secured by a rope going from the top of one of the posts to the point on the ground between the posts and then back up to the top of the other post. Where should the point at which the rope touches the ground be located so that the least amount of rope is used? All right, so that's what we're dealing with. Let's shrink this down so I can draw a picture. So for these types of problems, first of all, we have to decide, what are we trying to find? We're trying to find the least amount of rope. All right, so let's draw this picture. We've got two posts. One of them is 7 meters tall, and the other one is 13 meters tall. And ground in between them. And we want to put a point somewhere in the ground. And we're not sure exactly where this should go, but we're going to connect rope to the tops of each of the poles. So to there and to there. And so we want those two red segments, the length of those to be a minimum. All right, so that's the first step, is to draw a picture and identify what you want. And we also know that the posts are 25 meters apart. All right, so we're going to need to label this with some variables. Well, let's call this length of the rope A and this length B. Can't use the same variable, they probably are not the same lengths. And then we need to label parts of these right triangles which we're creating here. So let's call this part X, and then the other part we'll call 25 minus X. All right, so we want to use the least amount of rope. So what we need to do is we need to write a function which represents what we're trying to maximize or minimize. And then we want to find a max or a min of that function. So in this case, let's do this in, do it in red. We're going to write a function, call it f of x, and it's going to represent the length of the rope, or in other words, a plus b. So I'm going to do this in terms of x. So a in terms of x, well, if we use the Pythagorean theorem, a is going to be the square root of x squared plus 49. And for b, once again we'll use Pythagorean theorem, and b is going to be the square root of the quantity 25 minus x squared plus 13 squared. Alright, so now we have a function which represents the amount of rope. So that's the next step, is to make sure you can come up with that function and do it in terms of a single variable. Now we want to find a minimum. So how do we do that? Well, we need to find the derivative and set it equal to 0. So let's jump into our calculations. And then we want to verify that that 0 is a minimum, and then we'll be done. All right, so the derivative of this is going to be, with the chain rule, 2 root x squared plus 49. The 2's will cancel. So we get x over the square root of x squared plus 49. For the next one, with the chain rule, we're going to have 2 times 25 minus x to the first power, and then another chain rule times the derivative of 25 minus x, which is a negative 1, and then 2 times that giant square root, 25 minus x squared plus 169. And the 2's, once again, will cancel there. So we want to set this equal to 0. And solve that. So let's see, I can set it equal to 0, and therefore I can swing 1 to the other side. So basically we're trying to find when x over the square root of x squared plus 49 is equal to 25 minus x over the square root of 25 minus x quantity squared plus 169. Okay, so if, let's see, square both sides and cross multiply, I'm going to get x squared times 25 minus x quantity squared plus 169 equals x squared plus 49 quantity times 25 minus x. And it seems like this is going to be a lot of calculating, but if I could do this smartly, I'm going to notice, and this is going to be squared, because I'm squaring both sides first, then I cross multiply. All right, let me distribute the x squared on the left side. I'm going to get an x squared times 25 minus x quantity squared, and then x squared times 169. On the other side, let me distribute this. So I'm going to get an x squared times 25 minus x quantity squared, which is going to cancel with the other side, and then 49 times 25 minus x squared. All right, so that cancels out nicely. At this point, I could distribute. I don't feel like doing that. So what if I take the square root of both sides? I'll get the absolute value of 13x. And I know, by the way, well, we'll come back to that in a minute. Absolute value of 13x equals the absolute value of 7. Oh, and I don't need any absolute value there because I know these quantities. So 7 times 25 minus x. So I can just write, since I know x is positive, and that's something to think about right away. Let's go back to the beginning for a minute here. Let's think about any restrictions we have on x. Well, x obviously has to be greater than or equal to 0. If x equals 0, then that would mean that we put the point here, and then we'd have the rope going straight down the 7-meter pole, and then on a diagonal of a right triangle with sides 13 and 25. And then we know the biggest x could be is 25. So you always want to make sure you keep an eye on the domain, because once you start getting into the function, now we're just doing, calculus on this function and not thinking too much about the domain. So you want to make sure that you keep an eye on what are the restrictions on our domain for this particular application of this function. All right, so we're going to have x, this is going to be positive. So now let's solve this. We're going to get 7 quarters is $1.75, and then we'll add the 7x to the other side. We get 20x. So 175 divided by 20, 5 goes into that, 35 over 4, or 8.75. Now the units on our variable here, that was in meters. Now what you don't want to do is say, okay, there's your answer. Most of the time, yes, it's going to work out. But we need to verify that it's a minimum. So how do we do that? Well, we make a sign chart. So we have 8.75. That's the value of x. And then we know f prime is 0. So we need to take our derivative, which I guess is right over here, and let's pick a value smaller than 8.75. Let's, I don't know, pick, how about 0? When x is 0, which it could be, as I talked about the domain, or you could pick any number. You could pick 4, 6, 7 and a quarter, whatever. Plug it into your derivative. I can see that f prime of 0, though, is going to give me, my first fraction will be 0 minus, and my second fraction will wind up being a positive number. So I'm going to get a negative answer. And then if I pick a number bigger than 8.75, like let's say 25, then I'm going to get some positive number minus 0. So that's positive. So this tells me that f is decreasing on this interval, then it levels off, and then it's increasing, which means we have a local minimum. So our answer indeed is that. So let's go back up here in our picture. And so for the final answer, we should say, let's reread the question. Where should the point at which the rope touches the ground be located so that the least amount of rope is used? So the point should be located 8.75 meters from the 7-meter pole. You know, and it's this last little bit of detail that's important. So if you just solve this problem and you don't verify that it's a minimum or a maximum in another problem, if you don't verify that, you haven't completed the problem. And if you just left your answer as 8.75 meters, that's not really enough. I know someone can look at your picture and realize where that is, but you need to state that. So be complete when you're solving these problems. All right, let's try another one. A 4-liter container must have a square base, vertical sides, and an open top. So basically it looks like a box. Find the most economical shape which measures the surface area of material needed. So what do they mean by most economical shape? That's the first thing we need to figure out. Well, I guess in terms of spending money, you want to have the least surface area that would cost the least. So we want to minimize the surface area. So first thing we're going to need to do, as usual, is draw a picture. So we draw a box. As carefully as I can. There we go. And let's label this box. So it has a square base, so let's call that X and X. And for the vertical, let's just call that Y. Can't be X, it's not necessarily a cube. There we go. So let's write a function for the surface area. So the surface area, well, now I'm using X and Y. I have to convert that down to a single variable. Sometimes you could do it that way, or you could just say X, or you could just say S equals. And it's going to be the bottom, which is X squared, plus each of the sides. There's 4 sides, and the area of each side is X times Y. All right, so now we have a function in 2 variables. So we're not ready yet to find the derivative and set it equal to 0 and verify it's a minimum. So we need to think, what other information have they given us? Well, they said it's a 4-liter container. What is that? That represents the volume. The volume of this is X times Y. And we know that the volume is fixed. It's 4 liters, which is equivalent to 4,000 cubic centimeters. So 4,000 is equal to X squared Y. So that's a relationship that's going to be useful, because when I come back over to here, I need to write this surface area function in terms of a single variable. So I'll pick X. We'll call that S of X. And I'm going to need to replace any variable that's not an X. I need the parentheses here. 4 times X times Y. And if I go over to my other equation, Y is equal to 4,000 over X squared. So I'm going to plug that in. So now I have written my function that I'm trying to minimize in terms of a single variable. So now I'm ready to do the calculus. By the way, let's go back and think about our domain. Well, we know that X and Y have to be greater than 0. So they can't have negative values. Okay, so let's calculate the derivative. We'll set it equal to 0. We'll verify it's a minimum, hopefully. So we get 2x. So that's 16,000 over x, and so the derivative of that's going to be negative 16,000 over x squared, because that cancels with that, and that's x to the negative first power. Okay, so now we're going to set this equal to 0. And solve for x. So basically we've got 2x is equal to 16,000 over x squared, so we have x cubed is equal to 8,000. And that's a perfect cube, so x is equal to 20. Alright, so we're feeling pretty good. That's probably our answer. Now we need to verify. So make a sign chart. It's one way to do it. When x is 20, s prime is 0. So let's pick a number smaller than 20 and look at the derivative. So if I looking at right here, there's my derivative. If I plug in, for example, 10, I'm going to get 20. So let's stay organized here. So s prime of 10 is going to be 20 minus 16,000 over 100, which is 160. So that's a negative number. And then let's pick a number bigger than 20. How about 30? And we plug that in, and we're going to get 60 minus, well, actually, let's pick. I want to make my life more difficult and I have to use a calculator. How about let's pick 40. So that's going to be 80 minus 16,000 over 1,600. So that's 10. So that's going to be greater than 0. So therefore we know that my function s is decreasing, levels off, and then increasing. So we have a local minimum. So we verified, then we have the local minimum. Now, by the way, there is another way to verify it, and that would be looking at the second derivative. And so if I looked at the second derivative, now in the last example, calculating the second derivative would have been pretty ugly. So it was easier just to use the first derivative in a sign chart. Here, though, you can see if we calculate the next derivative, we're going to get 2 plus the derivative of that's a negative second. That's going to be a negative, so it's going to be a plus 1,600 times 2x over x cubed. So that cancels, that becomes an x squared. And so you can see that that's always, no matter what you plug in for x, that's always going to be greater than 0. And so therefore, s is concave up everywhere. And if the derivative at 20 is 0, we know that it has to be, therefore, s of 20 is a local minimum. All right, so as usual, we'll go back up here, reread the question, find the most economical shape. So that would mean that we need to give the dimensions of this. And so if x is 20, we get 20 centimeters by 20 centimeters. And then we have to figure out what y is. And I could go back over to here to solve, since that's already solved for y, and I'm going to get y is equal to 10, 4,000 over 400. So 10 centimeters. And so there's my final answer. So the general idea for all of these optimization problems, draw a picture if they don't have one, label the picture with variables, write an equation for what you're trying to maximize or minimize. And if the equation is not in terms of a single variable, use some other information from the problem or previous mathematical knowledge like Pythagorean theorem and things like that from our picture, and solve for one of the variables. So you can write your function in terms of a single variable, calculate the derivative, set it equal to 0, verify you have a max or a min, and then make sure you answer what the original question was asking for. All right, problem set 19b, page 527.